Alrighty, so I'm actually excited about today's lecture. There's a few things that I usually don't just do a single concept for every for every lecture, but this one I'm going to teach you a specific skill, and it's how to balance oxidation reduction reactions. And I actually think it's fun. And like I remember my mother would tell me she's like, oh, what are you teaching? I'm like, oxidation reaction. She's like, oh, I hate those. I'm like, I love them. And she's like, you're weird. So I know, my own mother thinks I'm weird because I actually enjoy this stuff, but it's puzzles. I mean, that's the thing, is if you think of it like chemistry, you're going to be like, oh man, do chemistry homework, yay. But these are just little puzzles, and they're fun puzzles. Well, at least I think they're fun. So, but before I get into oxidation reactions, I want to do some review. If you remember from last semester, assigning oxidation states. So oxidation states, there's a couple of ways that we track electrons. If you remember, we did formal charge. That's where you have each bonding species gets all of its lone pairs and half of its bonding pairs. And oxidation states, it's just a way of saying like, okay, these are where electrons are and these are where they're not. And I mean, the truth is somewhere in between formal charge and oxidation states, but there are some real effects of oxidation states. For instance, chromium plus 3. Chromium plus 3 is completely inert, and we put it in glass. We have it in paint. So there's some old paints that are chromium oxide. And then there's chromium plus 6. And chromium plus 6 is a carcinogen. It gives you a rash and it gives you cancer. So so oxidation states, like I said, do have real effects. So, but here are the rules. And these rules are hierarchical, meaning that rule number 1 is more important than rule number 2. So rule number 1, the oxidation state of a free atom or an atom in a free element is 0. So any element, copper, metal, chlorine gas, you can see these two, copper, metal, chlorine gas, oxygen gas, the oxidation state of those is 0, which means it has all of its electrons. And oxidation states that are negative mean they have extra electrons. Oxidation states that are positive means that they have fewer. So the oxidation state in a monatomic ion is equal to its charge. So monatomic, 1 atom. So calcium plus 2, its oxidation state is plus 2. Chloride is a -1 charge. It's a monatomic 1 atom ion. Chlorines is -1 in chloride. So then the sum of the oxidation states for all the atoms for a neutral molecular formula unit is 0. So water, for instance, is there, can be ionic compounds too, can be NaCl. So sodium chloride salt, the sum of sodiums plus chlorines, I almost said chloride, sodium plus chlorine and sodium chloride, the sum of those oxidation states is 0. And if it's an ion, it's equal to its charge. So nitrate there, so nitrogen plus 3 times oxygen's oxidation state, that sum equals -1, which is the charge of nitrate. And so rule number 4, alkali metals in compounds are always +1. Alkaline earth metals in compounds are +2. And then for everything else, there's this chart. So fluorine in compounds tends to be -1, hydrogen tends to be +1, oxygen tends to be -2. So halogens tend to be -1, oxygen family -2, nitrogen family -3. And it goes in that order. So meaning fluorine being -1 is more important than oxygen being -2. So, and that's just a review, but and this is what we're going to do today, how to balance redox reaction. So reduction oxidation, so shortened to redox. First thing you do is you assign every atom an oxidation state. Then you write and balance the half electrons for the electrons, and I'll show you how to do this. Balance the oxygens with waters and balance the hydrogens with H pluses. And then if you are balancing in an acidic environment, you're done at step number 4. If for a basic environment, you neutralize with hydroxides and then subtract the waters for an alkaline solution. So let's start with easy ones. So balance this redox equation. And at first glance, you're like, hey, it's already balanced, right? There's one aluminum on one side and one aluminum on the right side. There's one copper on the left, one copper on the right. Hey, we're done, right? This should be easy. Not exactly. And the reason is because the electron's flowing. So let me write the half reactions. So the half reactions are, you look at each element and you solve it only for the electron. So aluminum is going to aluminum plus 3, and this generates 3 electrons. So this first step, aluminum going to aluminum. So aluminum is going to aluminum plus 3, and in doing so, it generates 3 electrons. Copper plus 2 is absorbing 2 electrons to become copper metal. So you can see there that copper is going from copper plus 2 to copper 0 to copper metal. In order to do this, copper needs to absorb 2 electrons. And now because of this, aluminum is generating 3 and copper is generating 2. We have to balance the number of electrons. And so we have to look at the lowest common denominator of 3 and 2. And this is pretty easy because 3 and 2 are both prime numbers. So you have to multiply them. So the top one, the top equation, we have to multiply by 2. And the bottom equation, we're going to multiply by 3. So you can see now that 6 electrons are being generated and 6 electrons are being consumed. So we are generating 6 electrons and we are consuming 6 electrons. So we are now balanced in terms of electrons. So it's going to be 2, 3, 2, 3. So does this make sense? So recap for this one, we have this reaction here, aluminum metal plus copper plus 2 yields aluminum plus 3 and copper metal. So we need to balance this, and this is a oxidation reduction reaction. And you think, well, by atom, I'm already balanced, but that's not entirely the case, because aluminum going from aluminum metal to aluminum plus 3, and I guess I didn't even mention the oxidation states. Aluminum, metal, copper metal are both 0, and the ions are, they're equal to charge. So aluminum metal going to aluminum plus 3, going in this way, it generates 3 electrons. Copper plus 2 going to copper metal absorbs 2 electrons. So because of that, 2 and 3, that means that we need to generate 6 and consume 6. So we multiply aluminum by 2 and copper by 3, and then get the balanced equation that way. So is this making sense so far? So let's see if you can solve this one here. So hydrogen ion plus chromium metal goes to hydrogen gas and chromium plus 3. So I'm going to give you a hint. Chromium plus, oh no, it's the other way around. Chromium goes to chromium plus 3 electrons. What's the other half reaction? Can you think of it? So you can do it 2 ways. So you're balancing electrons here. You're going to go hydrogen ion plus 2 electrons makes H2, or you can do it that way. I like to think in whole numbers. So both of those are equivalent. Those are the half reactions. This one isn't as obvious with the hydrogen. That's a hard part here. That's why I gave you the half reactions. Some people think A, B, C. Or do you need more time? Are you stuck? Okay. All right. I'm going to come around the classroom. Tyler, Kiana, you guys doing okay?
Yeah.
So, reactions, chromium is generating 3 electrons. Hydrogen is consuming 2. So if you go to the lowest common denominator, 6, yeah. So top 1 by 2 to the bottom. Oh no, it's the. That's right. No. It's yeah, we need to six hydrogen ions to consume 6 electrons. Okay, so didn't hear the explanation. You probably didn't. It's C because lowest common denominator you have for these half reactions, you have 3 and 2. Lowest common denominator is 6. So you multiply this one by 2 and then this one by 3. And then doing so, you get C. Questions with this one? All right. Time to make it more complicated because it's more fun when it's complicated, right? So let's assign the oxidation states. I should have erased this. So for permanganate, so oxidation states for permanganate, it's easy. Oxygen's gonna be -2. So when we sum them up, -1 equals manganese plus 4 times oxygens. I put OX for oxygens because my O's and zeros are indistinguishable. -1 equals manganese plus 4 times -2. And 4 times -2, this is -8, added to both sides. 7 equals manganese's oxidation state. So does everyone get that? So let me write the oxidation state. That one's 7. So, and then when we do the half reactions, we're just balancing electrons in the half reactions. Let's do iron. Iron's pretty easy. iron plus 2, actually, no, go the other way, goes to iron plus 3 plus an electron. So iron going from plus 2 and goes to plus 3, it's being oxidized, meaning it's giving off an electron. Remember that about definition of oxidation reduction? Oxidation is loss of electrons, it's gain of oxygen, or it's loss of hydrogen. Reduction is the opposite. Reduction is gaining electrons, gaining hydrogen, or losing oxygen. So, and then how do we balance the manganese? It's going to be MnO4 minus plus 5 electrons goes to Mn plus 2, because it's going from, to go from plus 7 to plus 2, it needs 5 electrons. So to go from that plus 7 to plus 2, it's got to absorb 5 electrons. And the lowest common denominator now, so if iron is generating 1, manganese is consuming 5, that means that, oops, sorry. So iron is generating 1, manganese is consuming 5. That means we need to multiply the top equation by 5, right? Like so. So next step, we have 5 there. We need to balance the oxygens by adding water. There are 4 oxygens on this side, so we need 4 waters on that side. So, and now the last step is hydrogens. I'll go ahead and copy this. So now there are 4 times 2. There are 4 times 2 or 8 hydrogens. So you need 8 hydrogens on the other side. So 4 times 2 equals 8 hydrogens. So, right, there's 8 hydrogens on the right. So you need 8 hydrogens on the left. So you add 8 acids on the left to balance it. So now you can see everything is accounted for. 5 electrons are being generated, 5 electrons are being consumed. There are 8 hydrogens on the left, 8 hydrogens on the right. There are 4 oxygens on the left and 4 oxygens on the right from the waters. So, and it's done. So, and I got to try and slow down. I get excited doing these. I tend to go really fast. So the so here, iron goes from +2 to +3. So in doing so, it's going to generate an electron. Manganese goes from +7 to +2 in oxidation states. So that means 5 electrons need to be consumed in that, go from +7 to +2. So it's becoming 5 negative charges are absorbing from +7 to +2. So obviously then, so we have, so iron is generating 1, manganese is consuming 5, so we need 5 times as much iron. So we have 5 times as much iron. And after we do that, we can balance the oxygens. There are 4 oxygens on the left, there are none on the right, so we had 4 waters. And then we balance the hydrogens. There are 8 hydrogens on the right, so we need 8 hydrogens on the left to counterbalance it. And then when we have that, we have the balanced equation like so. So I would answer our questions. Is there any step that's difficult? Students have a really hard time with this, by the way. Permanganate.
Hey, Professor.
He-
Where did the,
oh, Actually, I'm answering the question. I'll repeat the question, but then please hold on to your thought, and I will get to you in a second, if you don't mind.
All right. All right.
Dennis, please go ahead, and I'll repeat the question. Okay. Question was for manganese +7. You only take into account the manganese. So the answer is, well, they're both important, but when you look at water, so oxygen is -2. When you go to water, here hydrogen is +1, oxygen is -2. Well, oxygen is not participating in the reaction electronically. It's staying -2. It's not being oxidized or reduced. So, and in calculating permanganate, so MnO4-, you use rule number 3, that the sum of the oxidation states in an ion equals its charge. Permanganate has a -1 charge, so you have -1 here, and there's 1 manganese, and there's 4 oxygens. I put OX for oxygens because my O's just look like zeros. So, and an oxygen tends to be -2. And so, yeah, solving for that. Does that answer your question, Dennis? Not really? And if you're thinking about the half reaction, if you're looking at the half reaction, so you only balance the electrons. You have +7 there for manganese, and go from +7 to +2, you need 5 electrons. And iron, likewise, to go from +2 to +3, an electron is generated. In the half reaction, what happens to the oxygen in the half reaction? You're only balancing the electrons. You're not balancing the oxygens. Actually, the book does it. If you follow the method in the book then would have you put 4 waters and 8 H pluses there. That's the way the book would do it, and you add them together. So the book does it a slightly different way. I change it into a different step. So the book does go ahead and balance it here. So Tyler, I'm sorry, would you please tell me what your question is?
I was gonna ask, where did the 4H2O came from?
Okay, so here is the steps, and I mean, so you assign oxidation states, write the half reactions. Now you balance oxygens with water. Okay.
Okay.
So what we've done here, step by step. So right now in this line, so we've done the half reaction. We've balanced the electrons. I mean this line there. So, and now obviously it's not balanced because we have oxygens. And in order to balance the oxygens, you add waters. And you add 4 waters because there's 4 oxygens here, and now 4 waters is going to balance the oxygens for those four oxygens in the permanganate and anion. Does that make sense?
Yeah, it does. Thank you.
Okay. Yeah, and then the step further, when you have the 4 waters, you've added 8 hydrogens, so you have to then take account those 8 hydrogens. Other questions? Students usually find this really hard, so forgive my exuberance, but I'm actually having fun. I got to slow down. I'm looking at the time like, man, I'm blowing through this. I got to slow down. I'll talk more slowly. All right, so let's see if you can solve this one. So permanganates, we've already talked about, and aluminum going to manganese +2 and aluminum +3. Yeah, go ahead, Dennis. Yeah. It's because we're gearing it towards batteries, and we tend to use aqueous solutions in batteries. And why can't it be carbon? It absolutely can. But I mean, here on Earth, almost everything is an aqueous solution, and we use aqueous solutions in batteries. So, question was, why do we always use water and hydrogen? Because and why can't we use like a carbon-based solvent? And the answer is you absolutely can. And but the thing is that here on Earth, I mean, almost everything is a aqueous water-based solvent, and all of our batteries we pretty much use water in. So with a few notable exceptions. So, but in general, yeah, here on Earth we do that, and you do it other ways, but we would have to change the rules for that. But these rules are for terrestrial Earth-based aqueous, which is typically aqueous solutions. That'd be a cool problem, though. The one that I've always dreamed about was what would you do if you have a planet that has liquid ammonia, and how would pH work and with liquid ammonia, and how would reactions work that way? That's the one that I always wondered what it would be like. That's Saturn, but it's nitrogen. It has a very dense atmosphere, denser than the Earth's, much denser than the Earth's actually. And it has nitrogen, not ammonia, and ethane and methane. So, but and it rains ethane there. I don't know about a moon of Jupiter that has ammonia. There's Europa, but that's ice. Europa is the other one that's of particular interest, but Europa has a thick ice shell around it. I think about Io too, but Io is just volcanic. And that might have ammonia in that, but that's, I don't know if it, yeah. Okay, so in class already voted, and the answer is D. So, and if you noticed, you can start like, I mean, I can do these pretty quickly. So lowest common denominator of 3 and 5 is 15. They're both prime numbers. So you don't always multiply them together, just as a caution. So, but I know we have been recently, but that isn't always the case. So it's going to be 3, 5, 3, 5, and you have 3 times 4 oxygens, so you need 12 waters, and you have 24 hydrogens, so you need 24 hydrogens on that side. So that's the way you would solve that one. So questions on this? So let's do this in an alkaline solution. So iodide plus permanganate goes to iodine and manganese dioxide. So let's look at, you already know that manganese is +7, and going to MnO2, this is +4. So manganese dioxide, so this is a neutral. So 0 is equal to manganese's oxidation state plus 2 times oxygens. Oxygen tends to be -2, which means manganese is going to be +4. So assigning the oxidation states, so manganese and permanganate is +7, manganese and manganese dioxide is +4, iodide is -1, iodine is going to be 0. So the way you do this is the same as you would an acid, but at the end you neutralize it. So let's go ahead and pretend like this is an acid. So do the half reactions. We have I minus plus certain number of electrons goes to I2. What's going to take, oh no, so it's not plus electrons, it's going to generate electrons. So I like to do it this way. So the charges are balanced that way. You can do it, as I mentioned before, you can do it that way as well, put a half. But I like to think in whole numbers like so, and manganese plus 3 electrons goes to MnO2. So to go from +7 to +4, 3 electrons have to be absorbed. And to do it step by step, so step by step, we have to multiply these by 3. Oh, no, it's gonna be 6. This by, because it's, so we need 6 iodides there, and then we need 2 there. My M is falling apart. Okay. So do you see the half reaction step? So now the next thing we do is we balance. I'll try and slow down because I know it's, sorry, I know I get excited. I'm so excited and I just can't hide it. So we've balanced the electrons with half reaction. Now we need to balance oxygen with H2Os. So we have we have 2 times 4 equals 8 oxygens. And we have 2 times 2 equals 4 oxygens. So we need extra 4 oxygen on right. So we need 4 waters there. Okay. So now, what the heck did I just do? So now we balance hydrogens. That's not really balance. We balance the hydrogens. And for hydrogens, there are 4 times 2 equals 8 hydrogens on right. And there are 0 hydrogens on left. So if there are 8 on the right and 0 on the left, we need 8 hydrogens on the left. So now the next step is, so this is balanced for acid. Now for base, we need to neutralize. So how are we going to do this? We're going to add 8 OH minus to both sides to get rid of 8 H pluses. So we're going to get 8 OHs on each side. And also remember, H plus plus OH minus, this forms water. So actually I need a new page. I added above or below. Okay. They're good. Edited below. Okay, so, and it's getting tight. So, let me get rid of, so we need to add 8 OHs to both sides. No, I'm getting out of space. Shoot. Okay. So we need to add 8 OH minus to both sides. So we've added 8 OH minus, and what's going to happen is, in doing so, these 8 OHs and 8 acids, they're going to form 8 waters, right? So These are going to go and they're going to form 8 waters. And now another step, there are 8 waters here and 4 waters here. So we need to subtract 4 waters from both sides. So meaning so subtract 4 waters from both sides. So that takes that away. And that goes to 4. And then I can move this over like so. Okay, and now I'm finally done. So now this is your final answer and it's balanced in alkaline solution. Okay, recap for this one. So balance this equation in an alkaline solution, basic solution. So first things first, get the oxidation states. Already mentioned manganese is +7 and permanganate, and calculate it out for manganese dioxide, it's +4. So iodide goes from -1 to 0. So 2 iodides is going to go to iodine, diatomic iodine, and generate 2 electrons in the process. Permanganate is going to absorb 3 electrons to go from +7 to +4 in manganese dioxide. So we balance the reactions. So we multiply the top equation by 3. So top equation by 3 and the bottom one by 2. And we get 6 iodides plus 2 permanganates yields 3 iodines and 2 magnesium dioxides. So we balance the waters. So there's 8 oxygens on the left, 4 oxygens on the right. So we need 4 waters on the right. And then 4 waters on the right means that there's 8 hydrogens on the right, so you need 8 hydrogens on the left. So now it's balanced for hydrogens, but this is an alkyl for acid, but this is an alkaline solution. So we neutralize it. Since there's 8 acids on the left, we need to add 8 hydroxides to both sides of the equation. So, and those 8 acids are neutralized to form 8 waters. And we subtract 4 waters that were already there on the right side of the equation to then get the full balanced equation right there in red. So, questions with that one? Students actually usually find this kind of tough. And so the questions, I get the most questions from the determining the rate law. Remember that with kinetics when we did determining the rate law? A lot of times students will leave this class and I can kind of see your face, Dennis. Like, I'm sorry if I'm trying to read your mind. You're like, you have that like, oh crap, kind of look in your face, which is fine. No, everyone feels that way. So, and it's just gonna take some time to sink in a little bit and try it a few times. Same thing with the determining the rate law thing. Students actually find that a lot harder than this one. So the determining the rate law, that's the worst. This is the second worst in this class as far as single problem concepts. So please. I mean, it's balancing it, right? I mean, you can whenever you have variables. I mean, so like 30 plus x equals y plus 15, right? So you can also write this as 15 plus x equals y. Like where did the 15 go? You know, it's just, yeah, it's just, it just goes away. It's just, yeah, It's part of our, since it doesn't participate, it goes away. It's a spectator, right? I mean, you can write any number of variables. You know, I could write alpha plus beta on both sides and they would go away, right? So mathematically speaking, when you have an equation, you can put whatever you want, but then the term balanced. So this is still a balanced equation, but you know, you can get rid of all that stuff. And it's also, I should say, this is a simplified, and it's also, I guess the other term is simplified. This is a simplified equation.
Hey, Professor, could you scroll up?
How far?
Oh,
Here?
too far, too far. Sorry, I tried to unmute it, but a little bit down, down, down. Okay, right there. Just trying to copy it.
No problem. I mean, the nice thing about having the iPad is I can, copy and paste, the lines very quickly.
All right, thank you.
You doing all right? You're not having the oh shucks moment? A lot of students do at this class, this lecture. Okay, and then usually what my students like me to do at this point in time, they just want to see me. Does anybody have any questions or anything? I usually just do a few more examples. Do I have other? Okay, and I can do, because I love doing these. I don't know. I know I'm weird. I love them for whatever reason. They're fun for me. So let's do some more. Iodide plus nitrate makes iodine plus nitrogen monoxide. So let's look at the oxidation states. So, or not, sorry, this is nitrite. I'm sorry, it's not nitrate, nitrite. So oxidation states, this is gonna be -1, this is gonna be 0. Now we gotta look at the other one. So for NO, 0 is equal to nitrogens plus oxygens. Oxygen tends to be -2, 0 is nitrogen plus and -2. 2 is nitrogen, so 2 is nitrogen there, and NO2 -1 is nitrogen plus 2 oxygen, -1 is nitrogen plus 2 times -2, 3 is nitrogens there, like that. So by 2 times -2 is -4, add 4 to both sides, you get 3. So now we do the half reactions. So 2I minus goes to I2 plus 2 electrons. NO2 plus an electron goes to NO. So you have to multiply the bottom one by 2. So then you have 2's there. And balance the oxygens. So we have four oxygens here. We have 2 oxygens here. So we need another 2 oxygens on the right. So 2 waters. So we have 4 hydrogens on the right. We need 4 hydrogens on the left. And we're done. So recap for this one: iodide plus nitrite makes iodine plus nitrogen monoxide. So do the oxidation states: -1 for iodide. Oh, this is going to be, I forgot the 2. That's a 2 there. I did mess up. So, so oxidation states. So for nitrogen monoxide, nitrogen's +2. For nitrite, NO2 minus, it's +3. So for the half reactions then are for nitrogen, it's going to be nitrogen dioxide. I'm sorry, what am I doing? The nitrite plus electrons. 1 electron goes to NO, the +3 going to +2. Then iodine, 2 iodides goes to iodine, generating 2 electrons. So 2 electrons are generated, so 2 need to be consumed. So we double the amount of nitrogen species. And in doing so, we balance the oxygens, 4 oxygens on the left, 2 on the right. So we need an extra 2 oxygens. So we had 2 waters. Now there's 4 hydrogens on the right, so we need 4 hydrogens on the left. And we're done. Too fast or? So B, ClO4 minus plus chloride mix ClO3 minus plus Cl2. Okay. This one here, assign the oxidation states. So ClO4 -1 is equal to chlorine plus 4 times oxygen. -1 is chlorine plus 4 times -2. 7 equals chlorine. ClO3 -1 is chlorine plus 3 times oxygen. -1 is chlorine plus 3 times -2. 5 is chlorine. So this is +7 and +5. So -1 and 0. So we have 2 chlorines, 2 chlorides, yielding chlorine plus 2 electrons. And then we have ClO4 minus plus 2 electrons yields ClO3 minus. So as you can see, we don't have to do anything. 2 electrons are being generated, 2 electrons are being consumed. So we can then do ClO4 minus plus, actually, for 2 chlorides, ClO3 minus plus Cl2. And now we have 4 oxygens on the left. So we need, no, we need an extra one. I'm sorry. I need 4. I need 4, but I just need 1. So we have ClO4, 4 oxygens on the left, ClO3, 3 oxygens on the right. So we need an extra one, extra water to balance off that extra oxygen. And then we need to have 2 acids to counterbalance that water. And then we're done. So are these looking easier or? Like I said, they're fun. It's not, this is not homework. This is not work. This is joy. This is absolute joy. There is no work in this other than the word homework, right? Love your job. You will never work a day in your life, as they say. So let's do the next one. Nitrate plus tin plus 2 makes 10 plus 4 plus NO. Man. All right, so already mentioned this one is plus 2 because we've already done nitrate. 10 plus 2, it's plus 2, and 10 plus 4, it's plus 4. So nitrate minus 1 is nitrogen plus 3 times oxygen. Minus 1 is nitrogen plus 3 times minus 2. 5 is nitrogen. So this is going to be plus 5. So our half reactions are NO3 minus plus 3 electrons makes NO, and then 10 plus 2 yields 10 plus 4, and then generates 2 electrons. So lowest common denominator of 3 and 2 is 6. So 2, 3. So we have then 2 NO3 minus plus 3, 10 plus 2 yields 3, 10 plus 4 plus 2 nitrogen monoxides. So now we have 6 oxygens, 2 times 3, 6 oxygens on the left and 2 oxygens on the right. So we need 4 waters to counterbalance that. And 4 waters means 8 hydrogen ions on the left. And we're done. So you want me to do more? We got 10 minutes left, 11 minutes left, unless you guys want to talk about something else. What's that? You got it. If you've got it, that means you're going to get all the questions right on the test for this one. Oh, there's only 2 questions, I think. But you have to balance them later on when we talk about, well, this is going to be electrochemistry. We'll start off here. And then, well, because usually, I don't know if you've noticed my teaching pattern. Usually when I introduce a chapter, I talk a lot about like the applications and what things mean. And I haven't done that for this one. This one we started as electrochem, and I jumped right into a specific skill, how to balance these things. And I always put a whole lecture towards it. Of course, I only have 3 of you here, 2 in Zoom and 1 in person. So normally I'm running around the classroom explaining things to students, but that's probably why I have extra time. So, which is fine. I mean, that and you guys are all brilliant, which also helps. So, so now I find myself with an extra 9 minutes. So I can keep on, like I said, I actually enjoy doing these. Do you want me to keep on going, or do you have another question, or do you even want to talk about anything? Yes. Okay. Yeah. Okay, question was this half reaction right here. If I were to take an NO3 molecule and add 3 electrons to it, would it actually make NO? Well, the answer is partially yes. What's going to happen though, if you actually do this reaction, I guess the answer is it depends. So it depends on the environment. If I were to answer the question most properly, the answer would be no, this is what the reaction would be. NO3 minus aqueous plus 3 electrons would yield NO gas, and then also plus 2 water liquid and 4 hydrogen. So if you're looking at the like what is likely going on in the in solution this way, but this is also the overall reaction. Part of it, I wonder if your question also was, is this part right here, is that absolutely possible? And even more so, the answer is yes, that is possible. You actually could take, like NO3 minus, like gas and like space, and hit it with 3 electrons, and it could go to NO. It would also then generate O2, or more likely like 2 oxygen radicals or something like that. It's unbalanced. It depends on the environment. So if this is like in deep space, yes, this is possible. You could have something like this going on. More likely though, it's that reaction there. That's more, and because when we're talking about this is dealing like with terrestrial, with here on Earth. And furthermore, the points of the half reactions are to keep track of the electrons. So the point of doing this is to make sure that the number of electrons that are generated equals the number of electrons that are consumed. So that's the whole point of this, that we're making sure that the balance of the electrons being generated and electrons being consumed, that the electrons are balanced that way. And then once we balance the electrons, then we balance the atoms, specifically the hydrogens and oxygens. So, but yeah, that's kind of cool though. That's a fun question. I'm picturing it in space and stars shooting out electrons and bombarding nitrate ions. That's astrochem. That's kind of a cool. Astrochem is, well, it's hard to do experiments with astrochem because like out in space, it's just there is so little matter, so little pressure, that in order to do that here on Earth, we have to like vacuum, like just have like really strong vacuum chambers, and then to see how it works. So they do some of that. Ralph Kaiser at Manoa does that. He does some astrochem. So like looking at that stuff. So those experiments are really hard just because they have to be because of the amount of vacuum that you have to have when you do them. And I did some of that, not necessarily for astrochem, but like bombarding things with electrons. I had an electron gun, which it was just it had a piece of tungsten. So you had just the current ran through a little piece of tungsten, and then I had 2 plates. And so you would run current through the tungsten, and then electrons would come off of that from the current, and then the plates, you would charge them and it would shoot like pew, the electron, like you would generate electrons, and then you would charge these plates and the electrons would fly in one direction. What's that? Yeah. Yeah, similar concept. But then you can even see the electrons. If you turned off the lights and looked at the vacuum chamber, you could see the electron beam coming out, which is it's essentially also known as a cathode ray. The old television sets, the cathode or the cathode ray tube television sets, work out the same principle, where you'd have a similar thing, an electron gun, and you shoot electrons off, and then they bend it, and then the electrons hitting the different spots on the screen is where you'd get the television signal. Like the screen is from the electron being generated electron gun, and then turned and shot towards the targets on the screen. And that's a cathode ray television set. So, well, the electrons striking the screen for black and white, it would just go black or white, or white or nothing. But then for color, there would be different, usually red, blue, green for most color TVs. It was just programmed in the image to strike and hit the different pixels. Yeah, yeah. Well, that's why when you put a magnet behind one of those TVs, it doesn't work anymore, because you mess up all the directions of it, and it behind the TV or also in the front on the screen, because then it would it would mess up all the targets where they would move a little bit. So when the electrons came, they wouldn't strike the target properly. Yeah, I remember those TVs. Those were fun. Well, not fun. I like the liquid screen, the LCD screen so much better. Liquid crystals. The way that the screens currently work, they're liquid crystal displays. The liquid crystals, there's a backing, there's a backlight, and then the liquid crystals, depending on the current that goes through them, they can change different colors. And so then you have the pixels of the specific liquid crystals, and then you just arrange it that way. I think see here, they're different crystals, or they change with current. I know it involves running electricity through the crystals, and then you have, like I said, you have a backlight. Because I had that happen on my computer. The backlight on my screen went out, and then you could kind of see it if you shine a flashlight to it, but that is basically the screen was junk. I had to get it replaced. Luckily, my warranty was still on for that. LED is the backlight is an LED. Same idea, liquid crystal, but because the original liquid crystal displays had fluorescent lights. The LEDs is the same concept, but the backlight is a light emitting diode LED. So you still have a different, you still have the liquid crystals though, having on the actual screen, like the one here on my laptop. The projector is different. You're putting light. Anyways, class is over. My shut up alarm is over, so I better stop recording.